Right. So we understood now the bridge learning process, right? But then nothing comes without challenges, right? So one of the challenges that happens during the learning process, we will look at now that we'll focus on that now. So if you look at here, generally you see that this is a star topology, right? And the only drawback of star topology is that if the central device fails, right, the entire communication fails. So, all these network administrators were thinking, come on here, I need to bring in some reliability here. Despite the failure of the bridge, my LAN has to function, my traffic has to go on, reliability has to be there. So people were trying to bring in, another backup device as a redundant, bridge, right? So that if one fails, another could be there and all this. But when they started to do like this, bring in redundancy, there were some problems. And one of the primary problem that we will learn is there is a problem called looping problem. Right. So what does your IEEE standard says, right? IEEE 802.1d says loops in the system must be prevented, which means when you bring in these kind of redundant bridges to just to increase reliability, right? If one malfunctions or not that, it's still the the LAN should be capable of communicating, right? So to bring in that redundancy, there is going to be a problem, and that problem is called looping problem. So we'll understand that what is looping problem, right? When does it happen, and how do you prevent that looping problem, right? So having said, if you want to create, reliability, right? You want to ensure reliability. So what people started to do is they brought in between every pair of LANs, right? If you can bring in a redundant bridge. So I'll show you a picture so that you can understand this. Now let's look at this particular case, right? So here, if you look at, there are two LANs, LAN 1 and LAN 2. And you see typically like a bus topology there. So there are two end systems shown in LAN 1 and two systems shown in LAN 2. But then now, unlike the previous picture that you saw, here you see two bridges, right? Bridge 1 and bridge 2. So from LAN 1 to LAN 2, if you have to go, right, you have two paths now. You can either go via bridge 1 or through bridge 2. So which basically means you have redundant paths. Right. So when this kind of a situation happens, where between a pair of LANs, you are not having just one route, but if you have multiple routes, this is where a problem happens. That problem happens only during the learning process, during the bridge learning process, which means we were talking that with the frame movements that's happening in the network, you gradually start populating your table, right? But then this redundancy is going to create a problem called looping. Okay, so let's understand what's happening. I just want you to before we get on and understand what's the problem that's happening, what is that loop? I want you to take to the subject called graph theory, right? As I've been repeatedly telling, computer networks, right, is basically an application of graph theory, where graph we model it as a set of vertices and the edges. So I'll typically show you a picture now here. So how is what is this vertices? What is the edges? Now say suppose I have four nodes. Okay. Now these nodes are connected, right? So what we call in graph is these are vertices, right? And the links that are connecting is called the edges. So we can model this graph beautifully for scenarios for computer networks, the transportation networks. Say for example, I'm in my home, right? I call this node as A, and I want to reach out to BIT, and I call this node as D, right? So I can either go through Vandalur route, right, or I can go through Kelambakam route. So the point now is I have not a single path, I have multiple paths. This multiple paths is what is going to create me the confusion. So when a graph is basically a set of vertices, right, connected by links, which is called the edges, right? So in transportation world, you see that the nodes are basically your places, are the points, right? And these are the roads, correct? And so now when you have multiple paths, right, is where the confusion happens. So you see that this is a closed circuit. That's what is called as a loop. Okay. So a graph generally has the closed circuit. So you have to resolve this loop, meaning you have to tell your algorithm a very defined way. Hey, come on here. If you have multiple paths, you have to go only through this one path. Which path will you choose? That is where the optimization comes in, right? So typically now what I do here is for every edge that we call in the graph terms, E for edge, or in our computer networks term, we call this as a link, right? We assign a weight value, right? So in graph theory, they call it as edge weight. In link, in computer networks, we call it as cost of the link, right? So we assign a cost value to this link. You want to travel from my home to say reach to Vandalur, right? It's going to take me some time. I need to, travel through some distance. So I can assign a cost value through this, right? So I say I assign a distance value to this. Now, if I want to go from A to V, it's going to take me around say 20 kilometers, right? And so from Mandalore, say to reach out to say VIT node D, it's going to take me another 10 kilometers. But then if I go through Kelambakam, right, that distance that's going to take here is going to be say 15 kilometers, right? From K to D, if I have to come in, it's only going to take me 5 kilometers, right? So now if your decision to travel, right, comes in by finding out a path which is basically going to minimize your cost of travel. So what you need to find out is the path cost. So what do you mean by path cost? Path cost is going to be, what is your path now? You want to go from A to D. You don't have a direct path. You are going either through this K node and reaching out to D, or via V node coming out to D. So there are two paths. But then you'll have to cross through these links physically, right? Which means you have to add the cost value of the individual link cost. So path cost, the definition goes like this. Path cost is going to be the sum of the link cost. Okay. So sum of the link cost meaning, 15 plus 5, which is basically going to be 20. In this case, it's going to be 30. So this becomes the shortest path algorithm, right? What do you mean by shortest path algorithm is you want to go from one node to any other node. What is the shortest path to reach? That is called shortest path algorithm. That's basically the famous Dijkstra algorithm, right? But then there is another algorithm called spanning tree algorithm. So don't confuse yourself with shortest path and spanning tree. Spanning tree is something like this, right? Now here in this case, you have four nodes, right? So spanning tree is basically find out the path such a way that you can reach out to all the four nodes without forming a cycle. Okay. So basically you wanted to connect, all these nodes, right? You have seen the physical representation here, but you want to reach out to all the nodes in such a way that the total cost is minimum, right? That is called minimum spanning tree. Okay. So anyway, if you can just understand the word spanning tree, that should be sufficient for this discussion. So spanning tree ideally here is you wanted to reach out to all the four nodes such a way there is no loops. So how are the ways that you can go on? You can either go like this, right? So this is one way, right? Or you can go through, so all the combinations you can start putting. So you can go like this, right? Or you can go the other way around, right? So if you look at this, so there are different ways in which you can travel, such a way that there is no loops there, right? So this is basically called a spanning tree. Why is that word spanning comes in here is you need to reach out to all the nodes, right? You need to span across all the nodes such a way there is no loops, which basically means that one single path. You are telling this is the path that you go to connect all the nodes, right? You don't create any confusion. So when you have multiple such spanning trees possible, among them, which one do you choose? If you can take the total cost value by traveling through all these links, and whichever is giving you the minimum cost, that becomes your minimum spanning tree, right? So having said here, now if I have to connect through, say, all these nodes, A, B, K, D, and all that, right? If I go through this, the total cost is going to be 20 plus 30, 20 plus 10 plus 5, which is going to be 35, right? But if I go through this particular route, right, it's going to be only 30, right? So this could be a preferred solution, right, where I connect all this. So this becomes a minimum spanning tree for me compared to other spanning tree solutions. If I go like this, it's going to be even more costlier, right? 35 plus 5, 40, right? I hope you're able to understand this, right? So the point now is in this case, now you're going from, you want redundancy. Ultimately, what is your solution? In case if bridge 2 fails, yeah, at least through bridge 1 it can go, or in case if bridge 1 fails, bridge 2 can operate, so that you have reliability ensured despite catastrophe happening. That is your ultimate goal. But then that is creating you a problem during the learning process. So we'll look at that problem first, and we look at how this spanning tree is going to help to avoid creating that loop problem, right? So first we look at what is this problem that is getting created when you have such kind of a looping issue. So here, if you look at, I modeled this LAN as a node, right, and two bridges here as B1 and B2, right, and the LAN another node here. So if you look at now, I have two paths to go. Now this two paths is only going to create me a problem, right, in the learning process. So what is that problem? Let's try to understand. Suppose say station A wants to, in LAN 1, wants to send a frame to station D in LAN 2. Okay, so what it's going to do, it's going to add the frame header, right, where it's going to add the source and it's going to add the destination. Since it's a bus topology, when this frame is transmitted over the LAN 1, it's going to be received by both bridge B1 and B2 via the port 1 respectively. Initially, you know that the learning process, the tables is empty in both these bridges. Each bridge has its own table, right? And the tables are empty. So when the tables are empty and both the bridges receives a frame, what are they going to do? They're going to look at the frame. They understand, bridge B1 understands that, hey, come on here, I'm receiving this from A. He's mapped to port 1. So let me add an entry in the bridge table. But I don't know where D is. So what I'm going to do now, I'm going to regenerate the frame and send it through only, I have two port in this, right? So I'm going to send it through the outgoing port, which is port 2. So when basically B1 sends this, right, it is going to be received by all the stations in LAN 2. It's also going to be received by bridge B2. Understand this. When bridge B1 is doing this, bridge B2 is also going to do the same thing, right? It also receives a frame. It understands that A is being mapped to port 1. Right, it does not know where D is, right? So what is he going to do? He's also going to do what similar to what B1 did, right? He's also going to regenerate the frame and send it through LAN 1, which is going to be received by all the devices in the LAN 2, including the bridge B1 via port 2. So now this is the problem, right? So what happens now is each bridge is doing its functionality independently, right? But both are doing the same thing, right? And so there is going to be two copies of the frame on LAN 2. And this two copies is where is going to create you the looping problem. Now, whatever bridge B1 is sent is going to be received by D. Obviously, he's going to maintain it, but then it's going to be also received by B2. So when B2 receives the frame, right, whatever B1 has sent, same copy, but it is receiving through another port now with the same header AD, right? So bridge B2 now will think, okay, I've got a frame now. This needs to be forwarded to D, right? And it is coming from the source A and I got it via port 2. So now bridge B2 will think, hey, come on here. Okay, A is sending from port 2. So I think A is mapped to 2. So let me go and update its table now from 1 to 2. I don't know where D is. So let me again regenerate and send it through port 1, right? So he will bridge B2 will do that. Similarly, B1 is also going to do the same thing. He got the frame now. He got it via B2, right? And the frame is received through port 2. He looks at the header and finds that, okay, I need to send it to D. I don't know where D is, but I understand that A is now is mapped to port 2. So I'll have to go and update the table now by changing it to port 2. And then let me forward it through the outgoing. So there's again going to be two copies of the frame on LAN 1. And it's going to be repeated, right? So what's going to happen now? This B2 is again going to receive it. Similarly, B1 is again going to receive it. And so this time what will happen now? He does not know where D is, but he thinks that, okay, A is now mapped to 1 because I got this frame via 1. So I'll go back and update it to port 1. And again, I'm going to send this, on LAN 2. So there's going to be, copies getting circulated to and fro back to LAN 1 and LAN 2. And it goes on, repeating this, unnecessarily creating traffic on these LANs, right? And this leads to something called as a broadcast storms. You're overloading the network with unnecessarily freshly generating copies and creating to and forth traffic on LAN 1 and LAN 2 just in your frame movements because of the redundancy created, because of this looping. So your traffic is getting looped around if you look at from LAN 1 to LAN 2 and it's not even stopping. This process is called looping. Why did this problem happen? It is because you created a redundant bridge. Between a pair of LANs, you had multiple bridges. And during the learning process, it is learning, right? Only through the frame movements. And when you start circulating these frames, right, what happens is that every time you receive a frame, you're going to learn and you keep updating. And so this has created the problem. So how will you solve this problem? Right now, that's the next question now, right? If you have physically removed the cables, the circulation is not going to happen. But physically removing the cables is not going to be the solution, right? I don't want to remove the cable because I created another bridge, redundant bridge, just to solve, right? In case if any bridge fails, the traffic on these lands should still go on. That is what is my ultimate aim. So I'm not going to remove any of this cable. But if I have a dynamic algorithm, right, which can resolve these loops by not physically removing the cable, right, but instead, disabling some ports in terms of not forwarding the frame, right, then you could contain this problem, right? So we are going to understand now how from a physical, the graph that you see, the physical topology that you see, which is basically having loops. But if you can ensure that, okay, we all coordinate such a way that let me disable this port, right? Whenever I receive a frame, let P forward it, let not K forward it. Okay, if you can bring in that discussion, right, implementation into your case, such a way that one of them is going to, one path you're going to go and not in the other path. That is where you resolve your loops, right, in your learning process. So that algorithm, that dynamic algorithm, which all the bridges are going to use together to create a loopless topology. So what do you mean by loopless topology? I'm not going to go and physically remove the cable. I'm only going to disable the functioning of some ports, right? So I'm going to ensure that the data flow is happening through only one path and not through other path, right? That algorithm is called as spanning tree algorithm. So our discussion now is going to get on of how you can ensure that spanning tree algorithm, right, that is going to be run by the bridges is going to ensure that, okay, when a frame is being sent, either bridge 1 or bridge 2 is only going to forward, right? And so if bridge 1 is sending it, bridge 2 is not going to forward it, right? How can you bring in that logic is where the spanning tree algorithm works in. So I hope you understood the context of what is a looping problem and when does a looping problem occurs and how we are going to resolve this looping problem when you have redundant bridges, right, to solve this problem. So having said, let's undergo this. So what is the problem we have now? Now, during the learning process, when you have redundant pair of bridges, right, it's going to create you broadcast stops. Unnecessarily, frames are getting flooded, which goes on to entirely hamper the performance of the network, right? It's going to bring down the entire network. So the solution now is if you have multiple paths from one LAN to reach out to other LAN, you should only go through one path. What is that path that you're going to bring in is going to be through the spanning tree algorithm. So again, IEEE 801 committee came up with standardizing the spanning tree algorithm. And here, what are we going to do is when you have redundant bridges, we are going to, this algorithm is basically going to automatically disable some bridge, right? And we are not going to physically remove any of the cable. What are we going to do is we are going to restrict the data flow in some, any of the bridge only and not in both the bridges, right? So which basically means that you're going to come up with a logical topology. Now, what do you mean by logical topology? You are restricting the data flow to flow in only some specific path and not through multiple paths. So you are not going to physically remove the cables. The cables are going to be there. Now you physically say, first you say your algorithm says go through bridge B1. But then later you understand that bridge B1 fails, you will automatically enable bridge B2. So bridge B2 will start to basically function and bridge B1 should be disabled. So we are not going to physically remove the cables, but we are going to make this automatically disabling the bridge. And we are going to automatically understand that some ports in the bridge is going to be not forwarding frames. We are going to block those ports, right? So we'll understand this problem of how spanning tree algorithm works. So what I require from all of you is this: have a notebook with you, right? We will now take up some scenario and apply spanning tree algorithm step by step. So any algorithm that comes in, we have to do the step by step implementation. And so we will come up with a loopless topology, right? And resolve this problem of broadcast norms that's happening because of the looping. So the requirement now comes in, right? So I'm going to take you to a picture. So before we understand the spanning tree algorithm, look at this particular picture. If you want, you can draw this, right? By pausing this video, right? You can draw this. So if you look at here, how many LANs, you see that these LANs are shown in dark lines. There could be multiple devices that are connected in this LAN, whatever topology. But the focus now is this. You see 4 LANs now. And right between every pair of LANs, you see that we have created some redundant bridges. We have added some redundant bridges. Why? Because we wanted reliability. But you know what's going to be the problem now if we have redundant bridges? But still, we want reliability. We want our algorithms to be dynamic to ensure even failures, we could still have the network functioning. That is our entire goal. So now let's look at this. Find out how many bridges are there in this extended LAN network that you see. What's your answer? So you see totally 1, 2, 3, 4, 5 bridges are there. And how many LANs you see? LAN 1, LAN 2, LAN 3, and LAN 4. So the question now that you see here is from LAN 1 to LAN 2, if you have to go from any device wants to communicate to any device in LAN 2, you see how many paths? You can go via bridge B1 or you can go via bridge B2. That's the direct path that you see, right? But there are also, indirect paths. So there are 2 paths in which you can go from LAN 1 to LAN 2 directly, correct? But now it's going to create you a looping problem, which you're aware of. Similarly, when you see from LAN 1 to LAN 3, how many paths you have? Calculate. Direct path, you see, okay, from LAN 1, you can go through B3 and then you can reach out to LAN 3. Or you can go via B1, reach out via LAN 2, then reach out to, so via, LAN 2, you reach out to B4 and reach out to LAN 3. Or via B2 through LAN 2, B4, you reach out to LAN 3. So there are 3 paths. Again, multiple paths. Say if you want to go from LAN 1 to LAN 4, you can go on to extend the discussion, right? You can go from B3 to reach out to LAN 4 directly. You can go through LAN 3 via B5 and reach out to LAN 4. So you have more paths now. B1, B2, then 4 paths comes in. Right? So between every pair of LANs, if you see, there are multiple paths. So when bridge starts to learn from the frame movements, obviously there is going to be broadcast storms, which is actually going to hamper your process. So how are you going to, resolve these looping problem? And how are you going to ensure that the bridge are going to function? And how are you going to ensure that despite failures, you can still have your network functioning? So we need to run a spanning tree algorithm. So for spanning tree algorithm, you have some requirements. Let's look at the requirement. Every bridge has a unique serial number, which we call as a bridge ID. Okay. So bridge B1 ID is 1, 2, 3, 4, 5. So these are the bridge IDs which are given you to ease understanding. Every bridge will have the serial number, right? So that serial number is what we're calling it as IDs. Having said that, every bridge has some IO ports. So the IO ports numbers are seen in brackets, right? So bridge B1 has 2 ports, port 1 and port 2. Similarly for this bridge B3, you see has 3 ports, correct? So every port in the bridge has a port ID or a port number. Is that okay? So having understood this, I hope we can now take the discussion of the algorithm one by one, right? So your requirement is that every bridge has a unique bridge ID and each port in the bridge has a unique port ID or the port number. So what is our goal now? We are going to run the spanning tree algorithm. So every bridge is basically going to exchange messages, right? Special messages, and it's going to identify, okay, now what should I do? Whether should I enable my ports or should I disable my ports? So for that, what are we going to do as a first step? All of you note down this step. The first step here is among all the bridges, how many bridges you see in this picture? You see 5 bridges, correct? So we are going to elect one of the bridge as the leader, right? So who's going to be the leader, right? So generally when we ask in a class who can be the leader, right? We always say one who has the, okay, let's sort all the register number. The first register number is going to be the leader. This is one way. Or you could say the one who's having the highest CGPA can become the leader. So there is some criteria in which you select a leader, right? Like that here among these bridges, one of them is going to be elected as a leader. And the leader who's going to be elected is the one who's having the lowest bridge ID. So can you now look at the picture and tell me who is having the lowest bridge ID? The smallest one, right? So you know that B1 is having the lowest bridge ID. So B1 now becomes the leader. So what we call here in the spanning tree algorithm, the terminology, B1 is called the root bridge. Okay. So what do you mean by root? I hope you all know the tree terminology, right? So whenever we say tree, right, what we have is, okay, there is a parent node and then there are child nodes and all this. So this parent node, the parent node is basically called as the root of the tree, right? Without the root, you can't have branches, right? So with respect to B1, we will look at the paths, right? We will look at how we can run this. So B1 is going to be called as a root bridge. And from there, we will resolve all these multiple paths issues. Okay, so the first step in the algorithm is selecting the root bridge. So among all the bridges, the bridge that has the lowest bridge ID becomes the root bridge. Now let's look at the second step. Okay, now every other bridges are there, right? Except the root bridge. Suppose you want to go from one bridge to reach to another bridge, to the root bridge. Which path will you go? That is what is the second step. So let's look at the second step now. So you have B1. Now through B2, B3, B4, B5, through these bridges, if you want to reach out to the root bridge, right? All these other bridges except the root bridge. From that bridge, if you have to reach out to the root bridge, which path will you take? Okay, that is the question now. So we are going to determine a path. So if you look at B2, you want to reach from B2 to B1. There are two paths in which you can go. Either through LAN 1 via port 1 of B2, you can reach out to B1. Or via LAN 2, right? You can reach out to B1. So there are two paths in which you can go. But then when you have two paths to go, right? The ambiguity comes. So the question now to be resolved now is determined, right? In which path you're going to go, such a way that is a least cost path. So what do you mean by least cost path? Now let's imagine that, okay, you want to go from this to this. How many hops it takes? Through this port 1, you're going and reaching to B1. It's only going to take one hop, right? You're just doing via port 1, you're reaching in one hop. So this path is also cost is 1, right? Which is basically what? Hop count. So you want to go from B2 to B1, the hop count is 1. If you want to go through LAN 1, hop count is 1. If you go via LAN 2, again the hop count is 1. Right? So there is a tie now. So I can either go via port 1 or port 2. Both the paths are least cost. So how will you resolve this tie now when you have a tie? So the question says when you have a tie, the tie arises only when you have the same cost path. You choose the port which is having the lowest port ID. Right? So what do you mean by that now? So now what are you deciding now is from every bridge, right? You want to reach out to the root bridge. So from B2, you want to reach out to B1, right? So how are you going now? If you go via port 2, it's cost 1. If you go via port 1, it's cost 1. So there is a tie now. So how will you resolve the tie? You choose the lowest port ID of that bridge. So that port through which you go on to LAN 1 is called as the root port of that bridge. Right? So what are you doing now? The second step is for every other bridge except the root bridge, you are determining the root port. What do you mean by root port? If you go via that port of that bridge to reach out to the B1, that will be the least cost path. Okay, in this case, you had a tie. So you chose port 1 because it has the lowest port ID, and that port is going to be called as a root port. So I'm going to mark in every bridge certain ports with some numbers. Okay, so B2, this port 1 is going to be the port in which I'm going to reach out to port 1. So that port I'm going to mark it as root port, mark it as R. Right? So this case you had a confusion, a tie. Right, but let's look at this. From B3, you want to reach out to B1. Can you tell me which path you can go? You can go via port 1, right, and reach out to B1. What is the cost value now? It is just one hop. You go via LAN 1, you reach out, right? So that is one path. But if you're going through other ways, if you're going through port 2, you go through LAN 3, you come to B1. So this is one hop. From B4 via LAN 2, you'll have to reach out to B2. So hop, what is the hop count value? You need to do 2 hops, right? Is this the least cost path? No. This seems to be only one hop, but this seems to be 2 hops. But if you go via B3 to reach out to B1 through port 3, how many hops it takes? You have to go via LAN 4, B5, you have to go LAN 3. This is another hop. From B4, you have to reach out to B1 through LAN 2. So you take 3 hops. Via port 3, if you go, it is taking 3 hops for you, right? Via port 2, if you go, it is taking 2 hops for you. But via port 1, if you go, it's only taking you only 1 hop. So what is the least cost path? If you say from B3, right, you want to reach out to the root port, then you say via port 1. So that port is going to be marked as the root port of that particular bridge. So what is the definition of root port? For every bridge, you want to reach out to the leader, you want to reach out to the root bridge, which is the least cost path. Right? So can I give you an exercise now? I want you guys to now, I hope you have drawn this picture. So go and mark all the root port, right, of all other bridges except the root bridge. I think we have already done for B2 and B3. We have marked the ports of that particular bridge through which we are reaching the root bridge in least cost path. Can you identify for B4 and B5? Just try it out. Yeah. So for B4, which port is going to be the root bridge? So you have 2 ports in B4. How are you going to reach out to the root bridge B1? Either through port 1 via LAN 2. The hop is just 1, right? So that's going to be one solution. Or you go via LAN 3, reach out to B3, and from B3 you reach out to B1 through LAN 1. So the hop is 2, which is the least cost path. Yes, port 1 of B4. So that port you will mark it as the root. Similarly for B5, which is going to be a root port through reach to root bridge, right? One is okay, you go via port 1, right? Which means you go via LAN 3, you reach out to B4. And then from B4, you go via LAN 2 to reach out to B1. So the least cost path, the path cost value is how much? 2. But if you go via LAN 4, go through B3, and then via LAN 1 to reach out, again, it's going to be 2. So now there is a confusion, right? You have 2 paths, right? And both the path cost value is 2. So which one will you choose? Now there is a tie. So how will you resolve the tie? If you have a tie problem, choose the port, right, which is having the lowest port ID. So which is having the lowest port ID? Port 1 is having the lowest port ID. So that port you're going to make it as root port, mark it as root. So now for every other bridge except the root bridge, you have found out the root port you have determined. So that is the step 2. Steps 2 says determine the root port of each bridge except the root bridge. So what is that root port? The port that is having the least cost path to reach out to the root bridge is called the root port. If you have a tie in selecting which port to choose, then you will have to resolve the tie by choosing the one with the lowest port ID in that bridge. Right? And so what did you do now? You were trying to find out the least cost path. How did you find out the least cost path? You have to take the sum of the individual cost of the links. Correct? We used a simple concept called hop count. How many jumps you need to do to reach out to your root bridge, right? And we took the sum of all the individual hops to get the path cost value. But if I assign, I go on to give a cost value, right? Say LAN 1, if you go, it's going to be 100 Mbps. Via LAN 2, if you go, it's only going to be 10 Mbps speed. Right? So if you have to go from B2 to B1, you prefer high speed LANs, right? You go via port 1 to reach out to B2 rather than going via low speed LANs. So if I can assign a cost value based on the speed of the LAN, right? That is going to be a better advantage. Say I give you a formula where the link cost formula is going to be, right? Say, the cost of the link, right? Divided by 10 power 8. So if you look at the cost of LAN 1 link, right, the speed of the link, right, so that's 100 Mbps that you have, right? So if I substitute the link cost value 100 Mbps divided by 10 power 8 in my formula, the cost value is going to be 1. right? But then if you go on to give the cost value of this LAN 2 based on the speed, then you go on to substitute 10 Mbps, right, by 10 power 8. So what is 10 Mbps? It's going to be 10 power 7 divided by 10 power 8, right? What is that going to be? It's going to be 10 power zero point 0.1, right? 1 by 10. So now what are you going to choose on? Are you going to choose the link which is having lower cost or a higher cost, right? So these ways you can basically come up choosing the case. So you have links choosing high, I'll have to change the formula accordingly. So let me reverse this. I think let's take the discussion like this. It's going to be 10 power 8 divided by, right, the link speed. This is the formula that I'm using to assign the cost of the links, right? So having said now, the LAN 1 speed is basically 100 Mbps, right? So if I substitute 100 Mbps there, 10 power 8 divided by what? 100 Mbps is what? 10 power 8. It's going to be 1. So I take the cost value of this LAN 1 as 1, right? Whereas if you look at LAN 2, what is the cost value that I'm taking now? Substitute the link speed value there. So 10 power 8 divided by 10 Mbps, right? 10 into 10 power 6, which is 10 power 7. So the cost value becomes 10. So if you go via LAN 2, the cost is 10. If you go via LAN 1, the cost is 1. So which one you prefer as the least cost? Via LAN 1 is being preferred, right? So what I did as a mistake here is I have to reverse this formula. So if I'm using this formula to assign the link cost value, then I would prefer high speed LANs, right? LANs which are having higher speed is given lower cost values. LANs which are having lower speeds are given higher link cost value. So obviously you prefer this. So there are multiple ways in which you can assign cost values. What I have taken for the discussion here is choosing hop counts. Very, very easy. Every link is being treated, uniformly as one, right? You go via this link, it's going to be one. You go via this, it's going to be one. But how many such links you need to pass through? That's where the hop count comes in. So I hope it's clear. So the step 2 is basically determination of root port of each bridge. Now what is step 3? Step 3 is this. Now we have identified what is the root port, right, to reach out to the root bridge, right? So we have marked all those port numbers of each bridge as the root port. The third step now is ultimately what is our goal now? From LAN 1, if you have to go to LAN 2, there is only going to be one path that you have to decide, right? So let's now look at this. You want for each LAN, right? From every LAN, you want to reach out to the root bridge. Through which bridge that is connected to that LAN will you go and reach out to the root bridge? That is what we are going to find out. So I'm going to give a name to this. We are going to select the designated bridge for each LAN. Right? So what is that meaning? So for example, now from LAN 1, if I have to go and reach out to the root bridge, how many ways I can go? I can either go through the bridge B5, which is connected to LAN 4, or B3 to connect to, which is connected to the LAN 4 to reach out to the root bridge. But if I go through B3, right, my frames go through B3 to reach out to B1, what will be the path cost? Tell me. Right? It's going to be right through B3 and then from through LAN 1, right? So it's going to be cost 2. But if I go through B5, right, which is connected to me through B5 and then through LAN through to reach out to B4 and then through LAN 2 to reach out to B1. So how many hops you take? 1, 2, and 3. Whereas if you go via B3 to reach out, it's only going to take you 2 hops. So which is the least cost path that you will prefer? Right? You will prefer going through B3, right, to reach out to your root bridge. So that bridge which you select for that particular LAN to reach out to your root bridge in least cost is called as the designated bridge. So what do you mean by the designated bridge? For every LAN, right, you want to reach out from that LAN to the root bridge. Through which bridge? What is the least cost path from that LAN to reach out to the root bridge? That you'll have to calculate. So through which bridge did you go? Right, in that LAN to reach out to the root bridge, that bridge will be designated as your designated bridge. So now I have two options, B3 or B5. I have chosen B3 as my designated bridge. And the interesting part is this. Now, which port in that designated bridge through which you reached out? So I went through port 3 of that designated bridge to reach out to the root bridge in least cost path. That port is called as designated port, right? So the LAN 4 through B3, you're reaching out to B1, right? Designated bridge. And the port in which you're connected to that designated bridge in that LAN is called as a designated port. Mark that port as a designated port. Okay, like that. Can you do for every LAN? So for LAN 4, I have identified B3 as a designated bridge, and the port in which I'm connected to the designated bridge route to reach out to the route bridge in least cost is port 3. I have marked it as 3. I marked it as D here. Can you now try for LAN 3? From LAN 3, if I have to reach out to bridge B1, tell me which is the designated bridge and which port is going to be the designated port. Right. So if you look at LAN 3, from LAN 3, if I have to reach out to the designated bridge, I can either go through B4 or through B3. So if I go through B3, what is going to be the hops? So 1, 2, right? Hop is 2. And if I have to go through B1 via B4, 1, 2, right? Again, it's basically going to be both are having the path cost as 2. So both are least cost path only. I have a tie now between B3 and B4, which bridge to choose. Both are having the least cost path. So what will you elect now? Which bridge will you elect as a designated bridge? When you have such ties between the bridges, which is connected to that LAN 3, then choose the bridge which is having the lowest port ID, right? So lowest bridge ID in this case, right? So in this case, you have B3 and B4. Which one will you select now? Right? Both are having the least cost path. So B3 is having the lowest bridge ID compared to B4. So then choose him now. Somehow we have to resolve the type when you have multiple paths. So I'm going to select B3 as a designated bridge for LAN 3 because that is having the lowest bridge ID compared to B4 because both I can reach out in path cost 2. So that port where I'm reaching out to the B1 is called as a designated port. So this port I'm marking it as T. So I'm done for LAN 3. I've done for LAN 4. Now what is all left over now? I have 2 more LANs. From LAN 1, if you have to reach out to the root bridge, which bridge is going to be a designated bridge? You are connected directly to the root bridge. So that is going to be a designated bridge. So the port 1 that you are connected to your designated root bridge is going to be a designated port. So you can directly reach out. Similarly, from LAN 2, if you want to reach out to your root bridge, obviously you are connected directly. So that port can be marked as designated port. So what we have done in the step 3 of the algorithm says from each LAN, right? If you want to reach out to the root bridge, through which designated bridge that is connected to that LAN to reach out to the root bridge, find out the least cost path and select that bridge through which you can reach out to the least cost path to reach out to your root bridge as your designated bridge. And the port that connects the designated bridge, right, to reach out your road bridge from that LAN is called as a designated port. And in case if you are having a tie between choosing your bridges, because both has the least cost path, then choose the bridge which is having the least bridge ID, right? And then resolve the tie. So once you have done this, we have almost come to the end of the algorithm. We have now identified in every bridge, right, what is all the root ports and the designated ports. Right. So what are we going to do now is there are some bridges where the ports are not put into any state, right? We are going to put those ports, right? We are basically going to disable that ports logically by putting it in a block state, right? So when I'm putting this into, what does it literally meaning is I'm not removing the cable. I'm only disabling the, functioning of that port by putting that into a forward state. Right? All other ports which are either marked as D and R, I am basically going to put that in the forwarding state. So what does it mean when I mark all the root ports and designated ports as forwarding state, meaning only those ports will be forwarding the frames. Rest all the ports which are not marked, right, which is being shown as dotted lines here. So I'll show you the picture now, right? So I see that these bridge 2, port 2 is being put into blocking state. Bridge B4, port 2 is being put into blocking state. Bridge B5, port 2 is being put into blocking state. So which means that we have now resolved the loops, right, by disabling the bridges, right, and specifically the ports by putting into forwarding state. Rest all ports which are marked as R and D, I have basically put it into forwarding state, right? So when now a frame from LAN 1 is coming, right, though both B1 and B2 is going to receive, Only B1 is going to forward the frame on the LAN 2 and not B2. You get the point, right? So typically is the case now, right? So what happens now because of this is you are reaching out, right, through only one path, right? Somehow it's going to be disabled. Now, if you want to reach out from LAN 1 to LAN 4, right, when you're forwarding this frame, right? So what happens is it is going to go through only one path here. Now, even if it comes through B5, B5 is not going to forward. So there is not going to be two copies that you're going to create. There's only going to be one copy of the frame that's going to be circulating, right? And you're ensuring that you, during your bridge learning process, the looping can be prevented. So what we have done through the spanning tree algorithm is basically to, go on to disable certain ports and put it in blocking state, right? Which can prevent this looping to happen. And hence you can create a loopless topology and your bridge learning process can be smooth and the frame movements can only take only a single path and not multiple paths. So that way you're basically resolve this and it's going to be periodically updated, right? So that even if say B2, B1 fails after some time, the B2 can now become, these ports could now become functional and they could disable, forward the frames through this, not through this. So this is an entirely and automatically updating algorithm where your spanning tree could be constructed in such a way there is only one path through which you can go, right? And so you can create the loops, problem that has been occurring when you have redundant pair of bridges. I hope you understood this. So how we can end this now is I just want you guys to try it out. So this entire algorithm has been taken from Leon Garcia, right? And there are references, examples even in Ferozon. So I want you to take up this, in your notebook, draw this scenario. And can we do this? Just run spanning tree algorithm in this case, step by step of what is explained, and then go through the step by step algorithm. And can you, once you've completed identifying the root ports, designated port, and which ports to be put into block state, the final state diagram, right? Can you just take a photo of it and share it in the WhatsApp group that we have with your register number? Right? Can we do that? I want all of you to, once you've understood this, just try out this with this practice example, run the spanning tree algorithm step by step, right? And finally, once you have achieved for identifying which ports to be blocked, right? Mark those ports, rest all the ports, whichever is root port and designated port, which is to be put into forwarding state, mark those and the final state diagram. Can you take a photo of it, right? And then share it in our WhatsApp group. So I'm going to count how many typically have understood and done this. Fine, guys. So thank you guys for your patience. Let's meet in our regular class.